All right, so let's go ahead and get started. So today we're going to start talking about some of my favorite material, and that's stereochemistry. It's an awful lot of what my lab does, and so it has a special place in my heart, if you will. And if you like putting puzzles together and like thinking about things in 3 dimensions, this is the chapter for you. So we're going to talk about stereoisomers, and we're going to try to figure out what in the world we mean by stereoisomer and how it differs from what we've already talked about, constitutional isomers. Okay? So stereoisomer is another layer of isomerism that you'll gain a very strong appreciation for as time goes on. We're going to talk about 2 molecules that you know quite well, starch and cellulose. And we're going to talk about what their differences are. And so how do stereoisomers compare in terms of their physical properties? I think you all will agree that starch and cellulose, they're composed of the exact same repeat unit, but they're very, very different, right? You're wearing cellulose. You eat starch, right? You do not wear starch and eat, well, you do eat cellulose, but it doesn't give you anything. It's just roughage, right? So we're going to talk about some of those things, and then we're going to start talking about chirality. And chirality is handedness, right? My right hand is very different from my left hand, and very similar at the same time, right? Some of us are right-handed, some of us are left-handed, and there's a reason for that, okay? And then we'll talk about a stereogenic center, which is a point of chirality, if you will, and we're going to figure out how we can identify stereogenic centers within a molecule. So the first thing that I want you to do is get out your model kit and get a single carbon atom and the 4 colored spheres. So you should have a blue, a white, a red, and a green colored sphere. And now what I want you to do is place those spheres on in random order. I've just thrown them up there like that, but just without thinking about it, place them in random order on the molecule. And I'll do the same thing. Okay? No sphere humor. All right. If we look at this, if everybody looks at what they made, it looks like we all made the same thing, right? I've got a single carbon atom with 4 colors attached to it, right? Constitutionally, they're identical. What I have and what you have is identical constitutionally. It's a carbon atom with 4 different colors attached to it, right? But let's look at this and see. So let me see your model. Now, if these are actually the same, then all the atoms or all the colors should line up, right? So if I do that, I can see that everything lines up 1 for 1, right? So you and I actually have exactly the same thing, okay? So somebody keep track of me. So that's 1 same. Let's look at Jessica's here. Uh-oh. I can get the green, the carbon, and the red to line up, but I can't get the blues and whites to line up. So did we make the same thing? We did not. So it's 1 alike, 1 not alike. Let's take yours. Let's see here. Can I get... Yep, we have the same thing. And we have the same thing. Let's see. We do not have the same thing. We have something different, yeah. So we can get the reds, the carbon, and the blues to line up, but your green and my green don't line up. And you made the same as... Yeah. Ours don't line up either, right? As I've got it here, so we have different. I think that one's yours. And if I was to go through, what we're kind of starting to see is that because it's at random, about 50% of you made what I had, and about 50% of you made something that I didn't have, right? And so that's going to be important in a future talk. But what's the difference between mine and Jessica's, for example? So if I take that, oh, I kept whose? I kept yours? So you've got mine? Okay. They all look alike. It's kind of hard to tell. So let's see. We did not have the same thing, right? We had the same thing. So whose do I have? Oh, well. So let's look at this one. That's fine. Right? So what's different? Right? That's exactly right. What else can you tell me? What's different about the red and the blue? They're all connected to the same carbon, right? But in space, they're pointing in different directions, right? Now, if I look at this and I take these, how would you describe the relationship as I'm holding them now? They're mirror images of one another, right? So if I imagine a mirror plane running right through me, right? Right through here, I would have a mirror plane. And so this would be my left hand, if you will, because I'm holding it in my left hand. And what's in the mirror? My right hand, that's right. Wake up in the morning, go to wherever you're at in your dorm, find a mirror, put your left hand up, and you'll see that the reflection coming back at you is your right hand, right? Everything has a mirror image, but not all mirror images are superimposable. And in this particular case, we have non-superimposable mirror images, okay? This molecule is different from this molecule, even though the atoms are connected identically, because what were they? The red and the blue were in different orientations in space, okay? And so it turns out that is really, really important, especially in biology, okay? Especially when we're talking about drugs, and we'll talk a little bit about that today as well, okay? So let's talk a little bit about starch and cellulose, okay? They are both sugars, okay? And if you look at cellulose on the left and starch on the right, you'll see that the atoms are connected identically, except what? The orientation of this sugar linkage, right? Notice this is an equatorial, because this is a six-membered ring, right? So this is an equatorial linkage. This is a axial equatorial linkage. How it's oriented in space is different. So tell me something that you know about cellulose. Okay. What else do we know about it? Is it tough? Pretty tough, right? It's also probably one of the most abundant polymers on Earth, right? All the plants, right, use this. This is wood, right? This is how we build our houses. You would not build your house out of starch. Same thing, constitutionally, but very different physical properties. What do you know about starch? You bake bread with it, it's in potatoes, you eat it, you get energy out of it, right? You eat a salad, it might fill you up, but you're still kind of hungry. You're not going to get a lot of energy from a salad unless you add all that other junk on it, like croutons and stuff, right? But the lettuce itself, not going to give you much other than some vitamins and minerals, and you do need a little roughage to clear you out. But, right, starch, bread, cellulose, salad, right? So what else do you know about cellulose versus starch? What about their chemical properties? Okay, we can digest starch. We can't digest cellulose, right? What else? What about solubility? Have you ever tried to dissolve a piece of paper? You've never tried that? You've never thrown a piece of tissue in the toilet? It doesn't dissolve away, right? But what happens to those starch packing peanuts that you get stuff in from Amazon or whatever, and you throw them in the sink, right? What happens to them when you pour water on them? They dissolve. But if you take a cellulose packing peanut and you throw it in the sink, it just gets mushy. It doesn't dissolve. So having a difference of equatorial versus axial equatorial, just changing this bond's orientation in space, makes all the difference in the world. And the reason is because cellulose takes on this sheet kind of structure. Because you have equatorial, it actually adopts a flatter shape, if you will, and it forms these sheets that interact by hydrogen bonds, and it's not very soluble in water at all. Starch, however, because you have the different bonds, you have the equatorial axial linkage, it will actually form a helix, and it puts all these hydrogen bonding groups on the outside, and it can form hydrogen bonds with water, and it will dissolve. Okay? You have enzymes that can process starch. You do not have enzymes that can process cellulose because of the different shapes of these molecules. So what's the take-home message here? Shape is everything. You will get into some higher level biology classes and some higher level biochemistry classes, and they will stop talking about shape. But shape is very important. Structure is function. Okay? It just is. You know, and so you need to know the basic structures of some of these things when you discuss them to truly understand what's going on. So again, you know, if we think about a starch like amylose, which we get from our grains and our breads, right? And if we hydrolyzed it, and by that we mean breaking these ether linkage that hold the polymer together, we get a unit of glucose. If we do the same thing with cellulose, which we can get from cotton, we get glucose. Both molecules are composed of glucose repeat units, or monomers, if you will. But they're connected differently in space. And so in one example, you get cellulose, the others, you get amylose. We know we can take cotton, we can make fiber out of it, we can wear it as clothes. I can take my clothes, I can go home when they're dirty, I can put them in the washer, and I don't worry about them dissolving away. If I had my shirt made out of starch, it would be a one-trick pony, right? I would wear it once, assuming it didn't rain, go home, try to clean it, it would dissolve away, right? And it's all because of just this change in one bond. So going axial versus equatorial makes all the difference in the world. And it's just how it's oriented in space. It has nothing to do with the elements. It has nothing to do with the repeat unit. It has to do with its shape. And that's what I want you to take away, is that shape or structure is function, okay? So now, there are two major classes of isomers. There are constitutional isomers, which we've already talked about, right? They have a different constitution, right? We have the same number and types of elements, but we connect them together differently. And so these so-called constitutional or structural isomers will have different IUPAC names, right? So I could give you a hydrocarbon that has the same number of carbons and hydrogens connected differently, but they would not have the same name, right? For example, you might have 3-methyl pentane versus hexane. Those are structural isomers of one another, but they have different names because of how the atoms are connected, okay? They have different physical properties, and they have different chemical properties. They may or may not have the same functional group. Stereoisomers, however, differ only in the way in which the atoms are oriented in space, just like with our model. The red sphere and the blue sphere for ours did not match up, right? They were oriented differently in space. But we would name it exactly the same. Her molecule and my molecule would be named exactly the same. How would we name this? It's got one carbon, so it would be a methane, right? So this is red, white, blue, green, methane. She would name hers the same way, red, white, green, blue, methane, right? But the way that things are oriented in space are very different, okay? And they always have the same functional group, right? If we figure each color is a functional group, my molecule and her molecule have exactly the same functional groups, okay? Now, the IUPAC names will only differ in certain prefixes, like cis and trans. Those are stereoisomers, okay? Cis, putting two things on the same side of the plane, or trans on opposite sides, right? But the constitution is the same. or R and S, which we're going to be talking about, which I think you already learned in the lab yesterday or this week, right? So R and S naming and cis-trans naming will be the only difference between stereoisomers, okay? A particular three-dimensional arrangement is called a configuration. So I have a particular configuration. Since I'm holding it in my left hand, I'm going to call it the left-handed configuration. Hers, since would be the right-handed configuration, right? But other than that, we've got the same molecule. Okay. So let's do a quick concepts test. Tell me, in these pairs, the green, the blue, and the yellow pair, are these constitutional isomers or stereoisomers? So what about the green? And how do I know that? They are connected differently. Will they have the same name? Name the one on the left for me, please. Okay, and it's what? 2,3-dimethyl pentane. And what's the one on the right? Pentane. Very different names, right? Same functional group. They're all both hydrocarbons, but you can clearly tell that the connection is different. How about the blue pair? They are constitutional isomers, right? Are the functional groups the same? What is the functional group on the left? An ether. What's the functional group on the right? Alcohol. So alcohols and ethers can actually form constitutional isomers of one another, right? And we see that. How about the yellow pair? Those are stereoisomers. They are connected the same. Ignoring cis and trans at this point, name the one on the left. One, 2-dimethyl cyclobutane. What's the name on the one on the right without taking into account cis or trans? 1, 2-dimethyl cyclobutane, excuse me, right? You can't distinguish those based on that name alone, so we need to have a way to distinguish them. So what would we put in front of the name for the one on the left? Trans, because the methyl groups are on opposite sides of the plane. How about the one on the right? Cis. So the one on the left becomes cis, or on the left becomes trans, excuse me, 1, 2-dimethyl cyclobutane, and the one on the right becomes cis, 1, 2-dimethyl cyclobutane. Okay? So if we look at 2-methylpentane versus 3-methylpentane, we can tell that those are clearly constitutional isomers, right? Very easy to do because they have a different name. If we look at our pair on the right, we see that these are stereoisomers. They have exactly the same name, right, except for the cis-trans designation. Okay? So we can clearly identify constitutional isomers versus stereoisomers based on their name. Okay? Now we need to get into chirality. Chirality, you all are familiar with this, you just don't know about it in terms of chirality. Okay, we've already talked a little bit about it with this molecule that we built. This is a chiral molecule. Okay? Everything has a mirror image, but not all mirror images are superimposable. Hers and mine are not superimposable. Okay? That clearly shows that we can have a mirror image that is not superimposable, right? And molecules are like our hands. Chirality actually means handedness from Greek. Okay? If I look at my left hand and I look at my right hand, I can see that they are mirror images of one another, ignoring any blemishes and defects that I have, right? But my right hand is not my left hand because I cannot superimpose one on the other. Right? Just doesn't work out. I don't have two right hands. I have a right hand and I have a left hand. And they are different, right? If I hold my right hand up to the mirror, I see my left hand. If I hold my left hand up to the mirror, I see my right hand, right? So we have this non-superimposable mirror image relationship. And that's exactly what we have when we have a carbon atom with 4 different things attached to it. Okay? Now, socks. Let's think about some real things in real life, okay? And these are socks without your toes, just normal old tube socks. They are achiral. They are not chiral objects because I can take my right sock, if you will, and I can perfectly lay it onto my left sock and everything matches up on a tube sock, right? So they are not chiral, and we say that it is an achiral thing. Okay, so if I can take an object and its mirror image and I can line them up perfectly, then it is not a chiral relationship. Okay? What about this brandy snifter? Is it chiral or achiral? Why do you say achiral? If I cut it in half, it's the same thing. You're correct. It is achiral. But why is it achiral? Yeah, so if I could imagine taking one and overlaying it on the other, everything would match up, right? All right. And it turns out that the brandy snifter, Yusuf, you're pretty close, there is a mirror plane that runs through it, right? So if I imagine a mirror plane running through here, the left side and the right side are related by mirror symmetry. And so this mirror symmetry actually makes this an achiral object, okay? And we'll talk a little bit more about that in a minute. How about a boat propeller? Is that chiral or achiral? Why do you know it's chiral? What makes it chiral? Then that would be achiral. Okay. Okay, why are they different? What makes a boat propeller and its mirror image non-superimposable? Yeah. Remember, a boat propeller, the blades come out and twist. They have a twisting motion to them, right? And I can twist to the right or I can twist to the left. And if you look at them, if you take the one where it's twisting to the right and you put it in the mirror, it's actually twisting to the left in the mirror image. And if you took both of those and you tried to superimpose them, they wouldn't. You'd get the hubs to line up, but the blades would be going in different directions. It turns out chirality matters if you're a fisherman, because if you get the wrong boat propeller and put on and you go forward, it actually starts to go backward, right? So it's kind of important that you have the right boat propeller on your boat for how it's geared, okay? Because theoretically, you can make a boat propeller having the blades go either way. It would work just fine, but the engine has to turn in the right direction to make it go, okay? So, oh, it'd go, but if you're going forward and all of a sudden you're going backwards, you know you put on the wrong boat propeller, okay? Oh, what happened there? Yeah, but that's not shears. I don't know. Oh, something's wrong with that image. So, scissors. Think about scissors. Are they chiral or achiral? And why are they chiral? Could I not make, what's that? There's right-handed and left-handed scissors. They have handedness, don't they? I can make a pair of scissors that have no handedness. They are those cheap little things that you give kindergartners that sit there and hurt your thumb and your finger every time you try to use them, right? Those are achiral. But a good pair of shears, a good pair of scissors, you make them for your right hand and they make them for your left hand, right? So if you go to the left-handed store, you can buy left-handed scissors, right? Most of the time, though, you go to the store, you buy right-handed scissors because more people are right-handed. How about a hammer? Chiral or achiral? Achiral. You don't know? Your gut's probably right. What's your gut telling you?
Flip it either way.
Okay. It turns out that if you look at a hammer and you turn it this way and you look at the claw, there's a mirror plane that runs through it, isn't there? That it makes the left-hand side of it a mirror image of the right-handed side. And so, yeah, a hammer is not chiral. And in fact, when you go to Lowe's and you go to buy a hammer, it doesn't have a list of right-handed hammers and a thing of left-handed hammers. Go into Lowe's and ask the guy, I need to find a left-handed hammer, and see how long it takes him to figure out which one's which, right? There is no left-handed hammer, right? Or right-handed hammer, at least not a hammer like this anyway, right? Because there's a mirror plane. You can use that hammer equally well with your right hand as your left hand. How about a baseball glove? It is chiral, right? Yeah, so if I take my right hand and I put it in my right-handed glove, it fits. If I take my left hand and try to put a right-handed glove on, not so much, right? I can stick my hand in there and jam it, but I'm not going to get the thumb to go where it needs to go and all that stuff, right? It's a problem. And so baseball gloves are chiral, okay? So now take your model. Okay, we've all got our model. And leave the white and the red on, but now remove the green and add 2 blues, and add another blue. And what you're going to find in doing this is that we all now have an identical molecule, right? So if I take Sarah's, everything lines up perfectly. There we go. Got it? Everything lines up perfectly, right? Everything lines up perfectly, right? Every one of us now have an identical molecule. So are these stereoisomers? No, they are not. They're just the same thing, right? That's exactly correct. We all now have exactly the same thing. So the take-home message here is if I have a carbon atom that is sp3 hybridized and it has 4 different things attached to it, it must be chiral. If I have a single carbon atom with 4 different things attached to it, it must be chiral. If I have a carbon atom that has 2 things that are identical, it's achiral. Okay? So when you go through and try to identify chiral centers, when you're doing your homework and stuff, the easiest thing to do first is to eliminate everything that's not chiral. And I always go through and I look for all the CH2s, because I know that those can't be chiral because they got 2 hydrogens, and I just cross them out. And then I start looking at the other carbons in the molecule, okay? So if we look at some other molecules, we see that water, H2O, it is achiral, okay? I can take one water molecule, the mirror image of that water molecule, but they will still superimpose on one another, okay? And guess what water has running right down through the middle of it? A mirror plane of symmetry, okay? Bromochloromethane, it too is achiral. Everything lines up, and it too has a mirror plane that runs right through it. It happens to be in the plane of the screen, right? So if this bromine atom is out of the screen and the chlorine is behind the screen, these 3 are lying in the plane of the screen. You can see that mirror plane running right through it, okay? So things that have mirror planes of symmetry are not going to be chiral, okay? In general, what do I mean by in general? Usually, but not always, okay? A molecule that has no stereogenic centers will not be chiral. Repeat that for me. A molecule with no stereogenic centers will usually not be chiral, right? All right. If we have one stereogenic center, a molecule will always be chiral. Just like what we built here. A single carbon atom with 4 different things on it is going to be chiral. It doesn't matter how much other carbon's on it. If it has only one carbon atom with 4 different things attached to it, it's going to be a chiral molecule. Okay? So if you see a molecule with a single stereogenic center, you know it's chiral, right? If a molecule has 2 or more stereogenic centers, the molecule may or may not be chiral. It gets a little more complicated there, okay? And achiral molecules will contain some type of symmetry, like a plane of symmetry, whereas chiral molecules do not. If you have a mirror plane in your molecule, it can't be chiral, okay? Now, it says that a plane of symmetry is a mirror plane that cuts the molecule in half. That does not mean that it has to go through an atom. The mirror plane can actually go through bonds. Okay? So you have to build a model. This is very important. You have to build models at this. I've been doing this for over 20-some years, and I still build models. Okay? I just build my models in the computer. I don't get my plastic model kit out. But you have to build models to see this sometimes, especially when you have more than one stereogenic center. Very, very important. Okay? So again, if we look at our bromochloromethane, we can see that plane of symmetry running right through here. And so since there's a mirror plane of symmetry, we know it's achiral. However, if I look at bromochlorofluoromethane, there is no plane of symmetry. It's going to be chiral. Okay? That's like our first model that we built with the 4 different colored spheres, right? And you can see the 4 different colors there as well. Okay? So where's the plane of symmetry? It's vertical, right? Yep, right through there. When we have larger molecules, we can have multiple stereogenic centers, and these become very, very important in drug manufacture, for example. Now, it is common to denote a chiral center by placing a star on it. Okay, so when you're doing your homework and you want to identify a chiral center, you just star it, okay, or put an asterisk, okay? This molecule, Darvon, it's an analgesic. What's an analgesic? It's a fancy name for what? Pardon? What'd you guess? Pain reliever. That's what it is. Yeah, analgesic, right? You get out of class, you got a headache, you're going to take an analgesic, all right? Now, this particular molecule has 2 stereogenic centers. So it may or may not be chiral, right? But it still has 2 stereogenic centers because this carbon atom is bound to 4 different things. What's it bound to? A methyl group. This group, which is clearly different than a methyl group. A hydrogen, and then this whole thing. Those are 4 different things. This carbon, it is stereogenic because it is bound to all this, which is clearly different than this, which is clearly different than that, and is clearly different than that oxygen atom. 4 different things are attached to those 2 carbons. So we have 2 stereogenic centers in this molecule. Ephedrine, right? If you need to take a bronchodilator or a decongestant, it has 2 stereogenic centers. Okay? Can you see those 2 stereogenic centers other than the fact that they're starred? Can you see that it's clearly got 4 different things attached to each one of those carbons? Okay? What do you know about ephedrine? What drugs? Meth. Yeah. Remove that OH group and you've got methamphetamine. That's drug synthesis. That's street drug synthesis. Street drug dealers are actually pretty good chemists. Okay? They just learn from some pretty scary people. All right? But basically they do a reaction to remove that OH. This is why you can't go into the store anymore and buy large quantities of Sudafed. Okay? That's why it's controlled, because it's very easy to convert it into an illicit drug. Fructose. This is a very simple sugar. If you like Coca-Cola, right? They use high fructose corn syrup or other soft drinks. Notice how many chiral centers are there. 1, 2, 3. Right? We have 3 different chiral centers. Nature only makes 1 molecule, though, this one, with the atoms in the correct orientation. Okay? So, if we look at this molecule, how would you name this molecule if this is an OH? 2-butanol, right? Butane is the parent, OL is the functional group for alcohol, and it's on carbon number 2. Now, if I look at this carbon, I can see that I've got a methyl group attached to it, I've got an OH attached to it, I've got a hydrogen attached to it, and I've got an ethyl group attached to it, right? And so that's what we have here. And I can see both mirror images. And if I take B and try to superimpose it on A, can it superimpose? No. And so 2-butanol is chiral. Okay? It is not an achiral molecule. We say that these are enantiomers to one another. A object and its non-superimposable mirror image are said to be enantiomers. So right-handed scissors and left-handed scissors are enantiomers to one another. Baseball gloves, the right-handed baseball glove and the left-handed baseball glove are enantiomers to one another. The hammer is just the hammer, right? Because there is no right-handed hammer nor a left-handed hammer, okay? So we say that these are enantiomers of one another. A is the enantiomer of B. B is the enantiomer of A, okay? There is also another element of symmetry that you need to pay attention to, and that's the center of symmetry. This molecule, it's a 4-membered ring. There's 1 carbon, 2nd carbon, 3rd carbon, 4th carbon, right? And it's got different things attached, okay? This is not a chiral molecule, even though you could argue that this carbon is attached here, which looks differently than that carbon back there, right? Because the red sphere is up where it's down here. They kind of look different. But actually, it's not chiral because there is a center of symmetry. It is a point at which we have a symmetry element. Can anybody tell me where that point is on this molecule? It's right in the very middle. So if I go from this white hydrogen through the center and go out an equal distance, I come to a hydrogen. If I go from this green chlorine and go to the center, go out in the same direction an equal distance, I come back to another chlorine. That's a center of symmetry. You cannot have in a chiral molecule mirror symmetry within that molecule, nor can you have centers of symmetry. Okay? And technically that means you can't have an improper rotation axis. But that's for another day and not in this class. That's the one element you technically can't have. But as a result of that, you can't have mirror symmetry nor centers of symmetry. And I think a lot of people see that a lot better than these improper rotation axes. Okay? So if we look at this molecule, right, is C1 a stereogenic center? No. Why not? Right, I've got a hydrogen, I've got a methyl group, but it turns out that this group is identical to this group, right? They just happen to be connected together. Another way that I would know that is what type of symmetry does that element or does that molecule have? It's got a mirror plane that runs through it, right? So if I imagine that the methyl group is coming out of the plane of the board and the hydrogen is going behind the plane of the board, I would have a mirror plane right through the center of the molecule, right? How about here, though? Yeah, we're chiral now, right? This is a stereogenic center. Because even though these two things are carbon, this is an sp2 hybridized carbon, this is an sp3 hybridized carbon. So this group is clearly different than this group. So we do have 4 things attached to carbon number 3 there, and it is a stereogenic center. One, 2-epoxy propane, which is really just an ether in a 3-membered ring, has a chirality center. Where is it at? Is it on carbon 1, carbon 2, or carbon 3? And why is it on carbon 2? And what are they? Right, so we have a hydrogen. What else? We have a methyl group. We have an OCH2. This one's going this way, right? And then we have a CH2O. And so this is a chiral center, okay? So we can have chiral centers being part of rings. They don't have to be part of rings. They just have to have 4 different things attached to that carbon atom, okay? Now, I want to talk a little bit about why this is extremely important. It turns out that chiral molecules behave differently under biological conditions because your proteins are chiral. Okay, and so just like I know that my right hand will only go into my left-handed glove, or in my right-handed glove, not my left-handed glove. The same thing here. So if you imagine all your proteins and your enzymes being right-handed, you could imagine that a right-handed molecule will fit differently than a left-handed molecule, and that could give different biological activities. It can give side effects. It can give all kinds of things. The famous example of this is the thalidomide incident that happened many years ago now. Okay? Thalidomide is a very simple molecule. It looks like this, and it has one stereogenic center. And it turns out, right, that if you take the mirror image, you'll see that they do not superimpose on one another. They gave this to pregnant women because of morning sickness. It's a very good anti-nausea drug, right? And women really struggle with this. I mean, during pregnancy, some of them have, violent morning sickness. And it's really, really a pain, right, to say the least. And so having a drug that could kind of ease some of that is kind of a good thing. And it turns out that thalidomide does this very, very well. However, it turns out that this mirror image is the anti-nausea drug. This mirror image, however, affects the fetus. It's a teratogen. And people were born with extreme birth defects. Shortened limbs, digits that weren't fully formed, depressed skulls. I mean, it was bad stuff, okay? So the drug industry has to determine today, the FDA requires this, if you have a molecule as a drug with a chiral center, you have to prove one of two things. You have to prove that you can make the enantiomer that only gives you the effect that you want, or if you're giving it as a mixture of both, because we can make mixtures very, very easily, okay, that the other enantiomer causes no harm. How difficult is it to prove that something causes no harm? Dang near impossible, right? And so one of the reasons why your drugs cost so much is because the drug companies have to make the enantiomer that does what it needs to do and leave the other enantiomer out of the mix. And that's not easy. When we were randomly putting those 4 atoms on at the very beginning of class, we got about what? About a 50-50 mix of peoples that look like mine and peoples that didn't, right? That's called a racemic mixture. It's an equal mixture of the right hand and the left-handed molecule. We can do that very easy. But that would also mean that you were giving a drug that had 50% of the enantiomer that does the work and 50% of the enantiomer that does not do the work and could be harmful. So how do we make a molecule where we have just the enantiomer that we want? That's tricky because we're trying to put those atoms on specifically in a certain orientation in space, and that's not a trivial task, okay? It turns out that even if you make the anti-nausea enantiomer, your body actually has an enzyme that racemizes this and makes the other one anyway. So you can't give thalidomide to pregnant women, period, even if it is enantiomerically pure, because your body will mess with it and change it to where you have a racemic mixture. If you look at sucrose, this is a simple little molecule, right? We use sucrose all the time. This is ordinary table sugar, right? You go into Starbucks, you want to put some sugar in your coffee. Look how many chiral centers there are. Making sugar in the laboratory without a plant, hard. Not easy to do at all, right? Because how many different configurations do we have at each one of these centers? We can either have the right-handed or the left-handed, right? So I can have right-handed or left-handed here, right-handed or left-handed here, right-handed or left-handed there. If I do this at random, it turns out it's 2 to the number of chiral centers, molecules that I would actually make. So 2 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. 2 to the 9th. Plug that into your calculator real quick. 2 times 2 times 2 times 2 times 2 times 2. That's a lot of molecules. And so if I was trying to make table sugar at random by putting the atoms together, I would end up with a mixture that contains that many different things, unique things. Huh? 512. So there are 512 unique compounds maximum that could come out of trying to make table sugar. Mother Nature makes one, right? She's really good at it. And so we're trying to figure out how to be good at that as well in the laboratory. Take Taxol. Anybody know the story of Taxol? This is what made Florida famous, right? This is why Florida, I can't remember if it's Florida State or University of Florida, but one of them really rich because they figured out how to synthesize Taxol, okay? Notice how many chiral centers. 2, 3, 4, 5, 6, 7, 8, 9, 10. About a dozen, if I counted right. There's 11. So 2 to the 11th. And there's this only one molecule is actually the anti-cancer drug. They figured out how to do that. That was tough. It's a multi-billion-dollar drug. They get royalties off of it. A little percentage off of multi-billion, a lot of money, right? And this is actually a very potent anti-cancer drug, especially for men and women with breast cancer. It's a very potent anti-cancer drug. But it comes from an endangered species of tree. To treat a few humans, we would have had to completely decimate the forest to get enough Taxol drug to do just a few rounds of treatment. That's not possible, right? So we had to figure out, nature made this. It is anti-cancerous, or an anti-cancer agent, but we got to figure out how to make it in the laboratory so we can make it on the kilogram scale so we can put it in the right dosage form and get it to the patients without having to decimate the yew tree.